All right. Hello, everyone, and welcome to today's webinar. Today we have Diksha Rastogi from Oak Ridge National Laboratory presenting on modeling climate extremes for impact assessment. Diksha has over 10 years of experience, over 12 years, of experience working in the fields of atmospheric and climate sciences. She's been working with the Computational Urban Sciences group recently, but she also worked as a research associate for the Computational Earth Sciences group at ORNL for several years before that. And yeah, I'm very excited to have her speak today. For your information, so my name is Andy Barris. I work at National Renewable Energy Laboratory. Today's session is going to be recorded and available on demand on YouTube later. If you have any issues hearing, you can try calling in using instead of using computer audio. Since it's a webinar, you'll be muted and off camera during the talk itself, but you can enter comments into the chat at any point. After Diksha has finished her presentation, you will be able to unmute yourself on demand when you have any questions. Diksha's presentation is going to be 45 minutes. So we can look forward to about 15 minutes of discussion after. So without further ado, Diksha, welcome to this webinar.
Thank you.
Actually, I forgot the AII credits. Sorry. I can't actually see the screen. There we are. So for the participants joining today, we did register the course for AII continuing education credits. If you would like to request credits for this webinar, you can find the information here. You can email info@aiaeb.org to receive credit after you have completed the course. All right, thank you, Diksha, take it away.
Thank you, Andy, for the introduction. Okay, so I need to, you need to unshare the screen so that I can share the screen.
Oh, so sorry.
No, you're fine, thank you. Let me share my screen. One second. Can you see my presentation in the screen now?
Yes.
Perfect. So first of all, thank you so much, Andy, for the introduction. Today, I'll be talking about climate extremes for impact assessment. So we all know that climate change is causing unprecedented impacts by increasing the severity and frequency of extremes, and also making them more widespread and persistent. Now, these widespread and persistent extremes can result in much higher impacts as compared to shorter isolated events. And I will give you some examples next. So for example, the Western US witnessed extreme high temperature during the September of last year. And this heat wave or extreme high temperature lasted about 12 days and caused record-breaking temperatures from across multiple states in the Western US, from Arizona to Washington. 61 million people were under extreme heat advisory, and this extreme event put enormous strain on electric grid, impacted human health, and fueled wildfires. Now, another example, which some of you may remember, are the below freezing temperatures that we witnessed during the Christmas break of last year. And this was witnessed by multiple states for multiple days. About 200 million people were under winter weather advisory, and nearly 1.5 million people were without power, and hundreds of flights were canceled. Now, these are just two examples, but we have been witnessing more events which are related to flooding, extreme precipitation, and wildfire, like the recent event in California. And we all know that these extreme events have increased during past decade and are projected to increase as our climate warms, which makes it extremely important to evaluate their characteristics now and how they are likely to change as the climate continues to warm. So the global climate models are the most scientifically sound tools to study climate and climate change. Now, first of all, what is climate? Climate is a long-term pattern of weather variables such as temperature, rainfall, solar radiation, and wind, etc. And these climate models can explain how these variables may change. So the global climate model can be defined as a complex mathematical representation of major climate system component and their interaction. And these components include atmosphere, land, ocean, and sea ice. Now, climate models divide the globe into a three-dimensional grid cell representing a specific geographical location and elevations. Now, each of these components, atmosphere, land, ocean, and sea ice, has equations that are calculated for these global grid for a set of climate variables, such as temperature. Now, in order to improve these climate models and further develop our understanding of climate change, there is an international effort called Coupled Model Intercomparison Project, which is an effort by IPCC, and it's called CMIP. So this, I think I skipped the slide. So the IPCC performed this assessment of using these climate models, and from first assessment report to the fourth assessment report, there have been tremendous improvement in the resolution of these global climate models. So from the figure on the slide, you can see the typical resolution of models in first assessment report was around 500 kilometer. And that in the fourth assessment report was around 110 kilometer or a degree. Now, currently we are in the sixth assessment of IPCC, and the typical resolution of GCMs in the sixth assessment is still around 1 degree, which is 110 kilometer, with a few models at half a degree. Now, this low resolution restricts the ability to accurately represent fine-scale features such as topography and govern local scale climate conditions. So, and we know that climate change impacts are witnessed at climate change impacts hydrological cycle, extreme events, electricity generation and use, urban system, and human health, to name a few. And to understand these impacts, we need high resolution climate information. So there's a clear mismatch of scale between global climate model output and the scale at which we need to understand these impact assessment. Now, why can't we run these models at very fine resolution? So the grid size of the model that we run is dependent upon the power of the computer that is available to solve these equations. The finer we go, the larger number of grids we have, and it requires bigger and faster computer to perform simulations. Therefore, there's a limit until which we can run these models which are run for the whole globe. So instead, we perform regional climate downscaling for regional to local scale assessment. Now, when we perform a regional model experiment, these models are run for a certain region and can independently resolve fine scale responses, such as those due to complex topography, coastlines, mesoscale convection, which are often poorly represented in the global climate models. So there are primarily two different downscaling techniques that are used in regional climate downscaling. The first one is dynamical downscaling. So this uses a physics process-based model such as Rexium or WRF. So first we select global climate models, and then we use a physics process-based model such as Rexium or WRF, and then we perform the simulations to generate high resolution output. Now, there are certain advantages of using this method. It provides a large suite of physically consistent variables. However, there are certain disadvantages as well. So this is computationally expensive experiments, and they are data intensive as well. So they require 3-hourly or 6-hourly input and for the 3D atmospheric layers, and they generate terabytes of output data. So it takes as well, it takes a lot of time to perform these simulation as well. So it has taken months and years for us to perform these simulation. Now, the second popular method is statistical downscaling. So in this method, we utilize the empirical relationship between GCM and observations. Now, this method is computationally efficient and faster, but there are certain limitations, such as it can only be done for a few variables based on the availability of good quality observations. Now, there's another major disadvantage of this method, which is the assumption of stationarity. We assume that the relationship between GCM and observations really stays stationary. But if the Earth system or the part of it evolves into a state which is significantly different from the present climate, this assumption becomes invalid. Now, for today's webinar, I'll be talking about two projects and then talk about an article that I recently published. So the first project that I'm going to talk about is the effect of climate change on federal hydropower, the third 9505 assessment. This project is funded by Water Power Technologies Office in the US Department of Energy. And the PI for this project is Dr. Shiche Kao, who is also at ORNL. Now, in this project, we use output from global climate models and perform climate downscaling on these models. And then we use downscale climate output to run hydrological models. And the output from which is further used to understand the impact on hydropower across the US. But for today's webinar, I'll just be focusing on the climate downscaling part. And I would like to acknowledge Dr. Shiche Kao and Dr. Mu'tazim Ashfaq, who I have collaborated with on this effort. So we selected 6 GCMs from CMIP6 archives based on their skills and availability of 6-hourly input. And then we performed downscaling to generate hydrological modeling inputs. And in this case, we perform both dynamical as well as statistical downscaling. So for dynamical downscaling, we use Rexium-4 and we downscale to 25 kilometer. And then we perform a daily correction using 2 different observations, Livne and Demet, to generate 4 kilometer output. In the second method, we used statistical downscaling using a method called DBCCA, and I'll talk about this method in next few slides. And then we used 2 different observations, Livne and Demet, to perform daily correction, and generate 4 kilometer output. So as you can see, we use 6 different models, 2 different downscaling technique, and 2 different observations. So this setup allowed us to understand the uncertainty that arises from the choice of downscaling technique and the choice of observations, as well as the choice of global climate models. Now, coming to the details of downscaling technique, as I was mentioning, I use regional climate model version 4, Rexium-4 for this downscaling. And we downscale down to 25 kilometer horizontal resolution. And we use 18 levels in vertical. And we use different parameterization and physics, which I will not talk about in details. And finally, we perform daily correction to bring the data down to 4 kilometer. Now, the statistical downscaling part was led by Dr. Shiche Kao, but I'll provide a brief summary. So for statistical downscaling, we use a method called double bias corrected constructed analog. In this method, we perform daily bias correction as coarse grid. So we bring all the global climate models to a common grid, in our case, 1 degree. And we also bring the observations to 1 degree. And we perform a daily bias correction using observations plus minus 15-day calendar days window. After daily correction is performed, we search for analogs which are closest for a given day using a plus minus 45 calendar day window. And we select 30 analogs. And then we determine weights for these analogs. Now we bring everything down to the final scale, which in our case is 4 kilometer. And then we construct these analogs. And finally, we perform another bias correction step to generate the final output. So in this method, there are 2 bias correction steps in the beginning and at the end. That is why this method is called double bias corrected constructed analog. To further explain it, so this is our first step, which we use original GCM, and then we perform a bias correction at the coarse resolution grid. And then we construct analog at finer scale, finer resolution, and then we finally perform a correction at fine scale to get the final output. So this is our input and this is our output. Now we use 2 different observations in our study. The first observation is David version 4. It is 1 kilometer. It is available at 1 kilometer horizontal resolution starting 1980 for the entire North America. And this is produced by Oak Ridge National Lab, Distributed Active Archive Center. Now the second observation that we use is Livne. Livne is available at 6 kilometer horizontal resolution for Conus, Mexico, and parts of Canada. And this product was originally produced by University of Colorado at Boulder, and now the updated version is available from UCLA. Now coming back to this framework, as I was mentioning that there are 4 downscale products, 2 based on dynamical downscaling, 2 based on statistical downscaling, and 1 for each observations, Livne and Demet. Now these 4 data sets have 6 members each for the 6 GCM. And given that we use two different downscaling technique and two different observation, we evaluated how they are getting impacted. The results are impacted by the choice of downscaling and choice of observations. So in next few slides, I will be showing you some evaluations. Now, in order to further evaluate, I have also used two other data sets. One is the CMIP6 raw GCM output, and the second one is the dynamically downscale output, which was as 25 kilometer. And for the purpose of evaluating against each other, I have interpolated them to 4 kilometer. So coming to historical evaluation, in historical evaluations, I have looked at 1980 to 2019 period. So in this slide, I'm showing you the 95th percentile of daily precipitation, or the magnitude of precipitation extremes. On left side, I have GCM, and followed by dynamically downscaled RECM. And these are again the mean of all the 6 members. And on top, I have Livney and Daymet observations. So I calculate 95th percentile for each day during 1980 and 2019, and then I create averages across all these years. I calculate 95th percentile for each year, and then I average across all these years, sorry. So as you can notice, the GCM underestimate the magnitude of P95, or extreme precipitation magnitude, over the southeast and the western US, while RECM shows some improvement, as you can see by the ovals that I have drawn on the presentation. Now, if we look at the statistically downscale and dynamically downscale corrected data set, which are shown by the middle row and the bottom row, they look fairly comparable to the observations, Livney and Daymet. And they are able to simulate the magnitude of P95 as well. However, I would like to note that there are marked differences between the observations, which trickle down to the downscale data set. And Livney and Daymet based data sets are different from each other, especially over the southeastern US. Now, in this slide, I'm showing you the evaluation of 95th percentile of daily maximum temperature, or the magnitude of temperature extremes. And again, I have GCM and dynamically downscaled RECM on the left, Livney and Daymet on the top, and then followed by statistically downscaled data set and dynamically downscaled data set. Now, GCM show warm bias in the magnitude of T95 over the south and cold bias over the higher elevations, whereas RECM shows cold bias at both over the south and at higher elevations. Whereas the statistically downscale corrected and dynamically downscale corrected data set are able to simulate T95 comparable to the observations. Now, moving on to some of the projected future changes. In this slide, I'm showing you the changes in P95, or the magnitude of extreme precipitation. And in this slide, I'm showing you the difference between future period, which is 2020 to 2059, and the historical period, which is 1980 to 2020. Again, I calculate P95 for each year, or 95th percentile of precipitation for each year. And then I average across the historical years and average across the future years, and I calculate the difference. On the top row, I'm showing you the projected changes in GCM, followed by statistically downscaled based on Livney observations and then Daymet observations. On the bottom, I'm showing you the dynamically downscaled data set, followed by dynamically downscaled corrected based on Livney observations and Daymet observations. And again, these results are average across all the 6 GCMs based data sets. Now, as you would notice that P95 is projected to increase across all of these 6 data sets, with the lowest increase projected by GCMs. Now, I would also like to note that the higher increase is projected by dynamically downscaled, that is the bottom 2 data set, as compared to statistically downscaled data set. And the third point that I would like to make on this slide is that the Daymet-based data set project higher increase in the magnitude of P95 as compared to the Livney-based data set. Now, in this slide, I'm showing you the changes in the frequency of temperature extremes, or number of days above historical T95. Again, I have GCM and then statistically downscaled data set. I have dynamically downscaled data set, and then dynamically downscaled and corrected data set. So in this case, I use historical T95 as the threshold in case of both calculating historical and future frequencies. So if you would notice, the statistically downscaled dataset project much higher increase in the frequency of temperature extremes as compared to the GCM, whereas dynamically downscaled dataset produce lower increase. However, the dynamically downscale corrected project increase, which is comparable to the GCMs. Now, some of you might be wondering, what are the causes of these differences? Why are these data sets so different? So the answer to that question is very difficult because these two data sets are based on entirely different techniques. So statistically downscale uses empirical relationships and dynamically downscale uses process-based model. So it is very hard to ascertain what could be causing these differences. However, using a large ensemble or a set that accounts for observations and different downscaling techniques is important to capture the range of uncertainty that may arise from these methods and observations. Now, in addition to using this data set for understanding the impact on hydropower across the US, we are also using this data set for other applications. And the first application that I would like to mention is the understanding the impact of climate change on building energy use. And this effort is led by Dr. Joshua New, who is also at Oak Ridge National Lab. So based on our data set, we are developing future typical meteorological year. And this data set is being developed for 18 cities across the US. And these are representative cities from each of the US climate zone and for all counties across the US. And this includes 9 weather variables, including air temperature, long wave, short wave, vapor pressure deficit, relative humidity, precipitation, wind, and pressure. And these files are formatted in energy plus weather format for the use in energy plus building simulations. And these will be used to assess how these climate projection will impact building energy use in future year. And in this case, they are using a statistical method to determine a representative year or representative month across all these data sets in historical and in future period. Now, the second project that I would like to mention is evaluating widespread and persistent climate extremes. And in this project, we are identifying extreme events which are widespread and persistent using a tracking algorithm. And we are primarily focusing on cold wave and heat waves. And we are trying to evaluate how these persistent and widespread events are going to impact our electric grid. So coming back to the project, the data set that I showed earlier in these in earlier few slides is already publicly available, and you can access that using the first link. And the data set for the future typical meteorological year for the 18 cities is already publicly available, and it will also be publicly available for the counties by the end of this fiscal year. We have a publication that focuses on evaluating how the choice of downscaling techniques and meteorological reference observation affect future hydroclimate projections in Earth's future. If you would like to get in more details of what I briefly explained in prior slides. The hydropower report, which is the ORN technical report, is already available for you to read, and you can access that using the first link. And we have also published a paper that on the evaluation of GCMs and how we sub-selected the 6 GCMs by a thorough evaluation over the conterminous US. Now, moving on to the second project. The second project is called Integrated Multi-Sector, Multi-Scale Modeling, and it is funded by the US DOE BER office. This project is led by PNNL, and again, this project has various components. It's a very vast and extensive project, but today I'll be focusing on the climate part of this project. And this climate effort was led by Dr. Andy Jones, who is at LBNL. And I would also like to thank my collaborator, Poya Vehmani, who is also at LBNL. Now, in this project, we performed downscaling using a technique called Thermodynamic Global Warming Approach, or TGW. TGW approach can be considered as a specialized form of dynamical downscaling. So basically, it still relies on regional climate models to translate large-scale conditions to smaller scale by leveraging the information from GCMs about future climate condition. So it first attempts to reproduce past sequence of weather events, and then applies a thermodynamic warming signal based on one or more climate model to examine how these events may play out in a hotter climate. So basically, instead of directly downscaling GCM, we first downscale reanalysis data. And then we modify the reanalysis data using a thermodynamic climate change signal derived from GCMs. And this modified reanalysis is then downscaled again in the same way as original data, which yields a simulation that can be interpreted as replaying past event in the context of future thermodynamic warming. And I will explain this in more details in the next few slides. Now, there are again advantages and disadvantages of this method. The first advantage would be it enables the best reproduction of known events of interest. We can isolate thermodynamic response using this method, and it allows event-based analysis rather than the climatology-based analysis. Now, there are certain disadvantages. The first one being most of these have been applied to a narrow time slice. So there's a question of generalizability with this method. Now, the second disadvantage is it doesn't capture the future dynamical changes, because dynamical changes, there are hardly any dynamical changes and they mostly remain unchanged. And the output is also limited to the range of observed variability. Now, in this project, we downscaled ERA5 reanalysis for 40 years from 1980 to 2019 using WRF down to 12 kilometers. And then we modified the reanalysis, ERA5 reanalysis, for two future periods, a near future, which is 2020 to 2059, and far future from 2060 to 29. And we modified it using a thermodynamic time series change signal, and redid these simulation for 4 times in each of these future periods. So we did a total of 8 future simulations. So 1 historical simulation, 4 in near future, and 4 in far future, following 4 warming trajectories. So to explain it a little bit more, the first line plot on the slide shows the average near surface air temperature over the US from 1980 to 2019. And then the remaining 2 plots show 4 more lines. So the historical time series is repeated 4 times in the near future and 4 times in the far future by imposing thermodynamic climate change signal based on the 2 emission scenario and 2 sets of global climate model sensitivities. And I'll talk about that a little bit more. So we use SSP 585 and 245 scenario. And I would like to mention that so historical event, for example, if we focus on the 2012, this is repeated in near future 4 times and 4 times in the far future at different thermodynamic warming levels. And these warming levels are again based on 2 emission scenarios, SSP 585 and 245, and 2 groups of global climate model based, whether they are low sensitivity or high sensitivity models. So how do we determine the low and high sensitivity model? We perform an evaluation of changes in temperature against changes in relative humidity. And then the models which are in show higher changes in temperature are grouped as high sensitivity model, and which have lower changes are grouped as low sensitivity model. And for each model, we use various ensemble member as they are available. So as you can see, we have 4 models in each category, and then we average across each ensemble member, each of these models, to create 2 more warming trajectories in addition to the SSP 585 and 245. Now, coming back to the weather research forecasting model that we used for downscaling in this project, we performed this downscaling to 12 kilometer horizontal resolution, and we used 39 levels in vertical. We used NOAA land surface model, and we used NLCD cover and for impervious surface data, and we used single layer urban canopy model for an enhanced representation of urban cover. And we used various cumulus and parameterization and physics schemes, which I won't get into details. Now, I would talk a little bit about how to use and interpret this data set. As I was mentioning, this data set is designed such that it provides an opportunity to understand how an often impactful and known event in the historical period, such as heat wave, cold wave, and etc., will play out if similar dynamic conditions were to occur in a future warmer climate. So the setup of this experiment provides us that opportunity, and I will demonstrate that with a few examples in next few slides. So in this slide, I'm showing you heat wave that occurred during June, and this slide just shows the June 29, 2012. There was a heat wave which was longer, spread across this day. The top plot on the left, the grid cells shown in purple are the grid cell which have an ongoing heat wave based on our identification criteria. And this heat wave was simulated once in historical simulations, which is shown just below that, and 8 times in future period, 4 in near future, which is the second column, and 4 in far future, and for 2 warming trajectories based on SSP 245, which is top and bottom, and 585, which is the middle rows. and two model sensitivity, which is low sensitivities are top two rows and high sensitivities are bottom two rows. Now, as you can notice, the spatial extent of the heat wave and extreme temperature during heat wave are projected to be higher during far future than near future. And they are more higher for SSP 585, which is the middle two rows, as compared to the top and bottom rows. And it is higher for high sensitivity model, which is bottom versus the top two rows. Now, to further explain this, we pick a grid cell which is around the center of this heat wave. In this case, we picked St. Louis, and we plotted the extreme temperature during the heat wave against the time. So you can see this is the extreme temperature during the heat wave in the historical simulation. And these four are the near futures experiments, these four, and then final four are shown at 2090 are the far future, the temperature during the far future. Now we plot these same values against the regional warming level to demonstrate how the characteristics of these events vary with different thermodynamic warming levels. So as you can see, as the regional warming increases, the extreme temperature during these events is projected to increase. Now, the next example that I would like to show is of a storm intensification. So this storm occurred during November of 2015, and the blue grid cell shows the grid point where that precipitation was above P95. And then this storm is simulated in the historical period and for 4 near future and 4 far future period. And again, for low sensitivity models, the top two, high sensitivity models, the bottom two, and SSP 245 top and bottom, and SSP 585 in the middle. And we find that the precipitation during these events are higher during far future as compared to the near future. Again, higher for SSP 585 and for high sensitivity model than 245 and low sensitivity model. So we average the domain precipitation and plot them against the time. And as you can see, the precipitation for historical is lower as compared to those for experiment in near future, which are lower than the precipitation during the far future experiments. Now we further plot these amount of precipitation against the regional warming level. And as you can see, this plot provides us details on how the characteristics of this precipitation event is changing under different warming level. Now in this slide, I'm showing you an example of Hurricane Irma, which occurred during the September of 2017. So on the top row, I'm showing you the observations and then historical simulations. So as you can see, the observation and historical storm track and precipitation compare pretty well. And then we have simulated it for the 4 experiment in the future, 2 near future and 2 far future, and 2 cold sensitivity and high sensitivity, and for SSP 585 scenario. And the total precipitation is shown in the box, and we find that the total precipitation during this hurricane event increases more so for far future than for near future, and in near future increases as compared to the historical experiments. So coming back to the project, so this data set is also publicly available. It contains 25 hourly and over 203 hourly variables at 12 kilometers. And this data set is available at this link, Jones et al. And the publication based on this data set is in review, and we have 2 of those publications in review. Now let's switch gear, and I'll talk about another study that we published last year. And this study focuses on understanding the impact of humidity, temperature on future electricity demand. So we all know that climate change is posing additional strain on electricity grid by modifying demand patterns and increasing the risk of power outages, primarily due to increased peak load during climate extreme events. Now, the co-occurrence of high relative humidity with high temperature level can increase human discomfort and thereby increase requirement for space cooling. Now, we have, in the past research, we have seen that relative humidity is generally projected to decrease over land in a warming climate. However, the combined impact of relative humidity changes and temperature changes is still not fully clear on heat stress and on electricity demand. So in this project, in this study, our objective was to understand the combined impact of rising temperature and humidity, changes in humidity on electricity demand. So before I talk further, I will introduce heat index or apparent temperature or feels like temperature. And it is used to understand the role of humidity on human body. So, and National Weather Service provide the heat index equation shown on the slide to calculate heat index or apparent temperature. If you focus on the figure on the slide, for a given temperature and humidity, for example, let's focus on 90 Fahrenheit and 60% humidity. The feels like temperature is 100 Fahrenheit, which is much higher than the temperature. Also, apparent temperature is much higher. What we feel is much higher than the temperature at 60% humidity. So in this study, we have used apparent temperature. So we use ERA5 hourly meteorological data, and we choose mean temperature, and then we calculate mean apparent temperature for 4 EIA regions in the Southeast. And then we also obtain US EIA hourly electricity demand, which is available by region. And we use this data set to understand how the electricity demand is likely to get impacted in a future warming climate. So we develop predictive models by establishing statistical relationship between average per capita demand and cooling degrees, which are based on population-weighted temperature and apparent temperature. To capture the correlation of energy demand with time-related variables, we use hours of the day, day of the week, and month as categorical variables. And we use the equation which I have shown on the slide. Now we perform develop two sets of predictive models for each of the 4 regions. One is based on temperature and other one is based on apparent temperature. And when we compare these models, we find apparent temperature model improves the RMSE compared to the temperature model for each of these 4 regions by anywhere between 7 to 11%. Once we have established that, we then apply this predictive model to a set of high resolution climate projections to understand the role of humidity in determining electricity demand in a warmer climate. So I will talk a little bit about climate projections that we used in this study. So the climate projection was developed at NCAR and are summarized in Liu et al. 2017 paper. They use weather research forecasting model and perform these simulations at 4-kilometer horizontal resolution. They use 13-year time period from 2001 to 2013. They first downscale ERA interim reanalysis, and they call it WRF control. And then they modify ERA interim reanalysis with a climate perturbation signal from CMIP5. So basically, this experiment is similar to the TGW approach that I mentioned in the previous project. And they have modified these variables in these experiments. And they have also used spectral nudging to make sure that they are not, we can understand the thermodynamic base changes and the dynamic changes remain unchanged. So these experiments are idealized setups. So they will allow for a comparison of certain events based on present and future warmer climate. And they also allow to isolate thermodynamic driven changes because large scale circulation mostly remain unchanged. So let's talk about some of the results from this study. So in this slide, I'm showing you the projected future changes in relative humidity, top row, temperature, the middle row, and apparent temperature, the bottom row. The red color are future and shows the future period, and blue color shows the historical period. So if you focus on the top row, there are small decrease in relative humidity shown by the mean line of the PDF. The middle row shows the increase in temperature during future period. And then finally, despite a decrease in relative humidity, however, the increase in temperature causes apparent temperature to increase as well. Now, in this slide, I'm showing you projective probability density plot for projected changes in electricity demand. The top row shows projected changes by temperature, and the bottom row shows projected changes by apparent temperature model. And then each column shows one region of EIA, one of the regions from the EIA. So as you can see, both temperature and apparent temperature model project increase in demand. However, the apparent temperature model project much higher increase in the demand as compared to the temperature model. Now, to further evaluate the role of humidity, we use bin of the data based on temperature quartiles. So the figure on the slide shows the scatter plot between relative humidity and difference in demand based on apparent temperature model and temperature model. And each color represents a quartile of future temperature. So blue is 0 to 25, orange is 25 to 50, green is 50 to 75, and red is 75 to 100. So what I'm trying to explain in this slide is that the humidity play an important role in amplifying electricity demand even during moderate temperature, future temperatures. So if you focus on the green and the orange dots and compare it with the red dot, which are the highest temperature quartiles, you can see humidity is able to magnify the demand even during these quartiles. Now at higher temperature, even low humidity can magnify the demand. No, so finally, in this slide, I am demonstrating the role of humidity during extreme hot event, and we are using 2020 as an example over the southeastern US. So during 2020, there was an extreme hot and humid heat wave over the southeastern US. The top plot shows the relative humidity. The second plot shows the percent of area under hot extremes, and the bottom plot shows the demand projected by temperature model and apparent temperature model. And you would notice that the bold lines are for future period and the dashed lines are for historical period. So first of all, let's look at the middle figure. So in the historical period, there was I should mention that the x-axis shows the summer period starting from the 1st of May to the end of September. So if we focus on the middle plot, you will notice that there was a heat wave that started towards the end of June and then continued in July and August. So there was a period of heat wave occurring from middle of the June to end of August. However, you can see there were temperature fluctuations, but in the future period, there's a constant high temperature during this period. Now, if we focus on the first plot, which is the relative humidity plot, you notice that there's a decrease in relative humidity during this period. Now, finally, if we focus on the third plot, which is the demand projections, the red color shows the temperature model-based demand, and the black shows apparent temperature. So as you can see that in the historical period, there was not much difference between the two models, but in the future period, the demand projected by apparent temperature is much more than temperature. So basically, the apparent temperature model is projecting higher demand generally. However, there's much higher increases during the extreme event, which is important because the extremes already have peak demand. And if they are going to be increased due to relative humidity in future, we need to carefully examine those differences. Now, to summarize, in this study, we developed predictive models by establishing statistical relationship between historical electricity demand and cooling degrees based on temperature and apparent temperature. And then we apply these predictive models on a set of high-resolution climate projections to understand the role of humidity and temperature in determining future electricity demand. We find that apparent temperature-based models perform better than temperature-based models. And we find that humidity amplifies the demand not only for highest temperature quartiles, but also for moderate temperature quartiles. So given that this is happening for moderate temperature, so we are likely to see these peaks outside the peak season for hot extremes. So that's all I have today. And thank you so much for your attention. I would be happy to answer any questions you may have.
Diksha, at the bottom of your screen, you should see a Q&A portion where there should be a couple of questions for you.
Okay.
Yeah, and I can moderate that, I think. Before we go to Q&A, I was asked to provide a correction on the AIA credits. So these days, you actually have to email events@ibpsa-usa and include your EIA member number to receive credit for the course. And then maybe Christine or Courtney can put that in the chat.
Yes, I will do that too.
Okay.
So I'm looking at the questions and I see where can I download the climate projections? These projections are, and they say from anywhere in the world. So you can download from anywhere in the world. And I have provided, so you can go to my Google Scholar. We have the data citation in the Google Scholar, so you can check it over there. And so the data set for all of these studies is publicly available and you can easily download that. I mean, it's a huge data set, so it may not be as easy because of the volume of the data, but it is publicly available and you can download that. there's a question that says, will future machine learning techniques be able to better produce climate predictions? That's a very good question, and there's a lot of research going on. I myself have been working on a couple of such studies, and I hope that is true. And however, I feel at this stage that machine learning model is as good as the data. So I'm not sure how we can bring in the uncertainty that comes with climate change in the machine learning models. So, but I assume that with the advancement in machine learning, we should be able to figure out ways where we can better predict climate. There's a question that says there might be uncertainty in the whole variables. I'm not sure what do you mean by whole variables. I'm assuming you mean precipitation, temperature. So yes, I mean, these are projections, so they are uncertainties. That is why we use different techniques and different observations so that we can capture these uncertainties in as the climate warms. So there's a question that says, is it possible to convert FTMY for all three time ranges to energy plus input? So I myself, I'm not working on that project. Dr. Joshua New is, and I would defer that question to him. You can email him to ask that question. And in my opinion, that it is data computationally intensive. That is why the FTM files are created, but I'm pretty sure it can be converted for all the three time ranges. But I think they have converted for the, I think they have one across all the future year. I have to check, but you can email Dr. Joshua New at Oak Ridge National Lab, and he should be able to answer your question.
Yeah, thank you.
So when can we expect FTMY files for other cities apart from 18 cities? So we are not, we haven't worked on other cities, but we are working on counties. So we will be providing files for each counties, and that will be available before the end of this fiscal year, which is I think we should be available by September. So yeah, should be able to download the county level files by September. There's a question that says, what parameters can be provided by downscaling efforts in addition to temperature? I'm interested in precipitation, relative humidity, solar radiation, cloud cover. Yes, all of these are available from the downscale output. And so for the second project, all of this data is already publicly available at 12-kilometer horizontal resolution and 3 hourly and hourly variables. You can see the list of the variables. For the first experiment, right now we have temperature, precipitation, daily data available, but if there is interest, we should be able to make other data available as well. I just see another question. The future TMY files project extreme weather as well. So I think this is, they are representative. So I guess they capture the mean more than extreme. But again, I would defer this question to Dr. Joshua New because he's the one who has been working on that. There's another question on the FTMY file, and it says, are there plans to scale to make available for all WMS station on Energy Plus website similar to existing files? I am not sure. I will have to ask Dr. Joshua New to make sure what he has in future for these files, like if they are going to do it for other stations. I will have to check with him. Yeah, I think I have all the questions answered. I'll be happy to answer any further questions.
All right, I'm seeing a lot of clapping and confetti emojis. Let's give everyone another minute or so to submit additional questions. In the meantime, I'm going to run through our end of webinar script real quick so I don't forget anything important. So As mentioned earlier, if you would like to receive AIA credit, please email your AIA member number and info that it was this webinar that you attended to events@ibpsa.us. The email for that is also in the chat. Still no questions. If you enjoyed this webinar, please consider joining the ibpsa-USA Research Committee. We have a working group specifically focused on finding speakers for webinars and organizing these webinars, running them like I am doing right now. I think the correct email for that is research@ibpsa.us. And there's also a link that will be pasted in the Zoom chat shortly where you can find more information. If you're watching this on YouTube later, or if you want to watch it again to find it on YouTube, you can find the ibpsa USA channel. Please like and subscribe, as one does. And I hope you join us next month as well. We have another exciting webinar coming up, which I have to confess I don't have the info on my screen right now.
I see a hand raised. Are they trying to ask a question or?
Yeah, if you have your hand raised, please go ahead and ask your question.
I think perhaps that was by accident.
Okay.
Not a problem, thank you.
Well, if nobody has anything else to add, Diksha, thank you so much for that wonderful presentation. Thank you, Andy, for moderating, and thank you everyone who was able to take the time out of their day to attend today.
Thank you, it was a pleasure.
Yes, thank you very much. Also, our next webinar is going to be on April 20th. We will have Zachary Bersola presenting on identifying emission reduction pathways for cities using ubem.io. So I hope to see many of you at next month's webinar. Again, Diksha, thank you very much for your really interesting presentation.
Definitely.
And I hope everyone has a pleasant rest of their days.
You too.
Thank you so much.